a record of our transactions. They're transactions. Let's see if I go to speaker view and I go to Sumatra. I think that's not the Sumatra I want. So the Sumatra I want is this one. Oh, it doesn't switch over. Can I close the other one? Yeah, okay, now it's forced. Chapter 6, angle measure. So let's talk about that. Let's just get that out of the way. We want to get radians on the table. So when we form an angle, right, we take the initial side OA and rotate it about the vertex O to the terminal side OB, and that sweeps out this thing we call an angle, right? And positive angle is swept out in the counterclockwise direction, and a negative angle in the clockwise direction, which is completely arbitrary. It's just the way it is. Angle measure. So here's their definition of radian measure. Let me see if it agrees with mine. A circle of radius 1, if a circle of radius 1 is drawn with the vertex of an angle at its center, then the measure of this angle in radians, abbreviated rad sometimes, is the length of the arc that subtends the angle. I disagree with this. Sorry. It's numerically equal to the arc, but it's not a length at all. A radian is not a length. So this is a problem, right? It's sort of a very important notion. And it's the first thing in chapter 6 that we encounter here. Are we looking at this? What are we looking at? Yeah, okay, sorry. There we go. I want to make sure I'm not off screen here. Can I also, yeah. So, yeah. So why do I disagree with this? Well, what it really is the ratio. So let me go to my pencil and paper here and give you my definition of radian measure. And I don't know. I don't think I'm a weirdo in this regard. So definition. The radian measure of an angle subtended by an arc A. This word is arc. Oh, sorry, I'm not showing you what I'm writing. Oh, here. Oh, my camera's all wampus because I was doing something else. All right. Yeah. How's that? Okay. So the radian measure of an angle subtended by an arc A in a circle of radius R is the ratio of R A is the ratio, and we'll call it theta, okay? And it's going to be the ratio of A to R. And so let's draw a picture of that. So here's a circle. And now we're not assuming here that it's the unit circle. Okay, that's the other thing the book does that I think is improper here. It assumes that we're in the unit circle. And we are not necessarily in the unit circle anymore. Okay, so this is a circle of radius R. Okay, so that's also an r. And I'm saying that this arc has length a, and theta is equal to the ratio of a to r. Now, the trick about this is that that is invariant. It's the same angle, the same measure in any circle. So why is that? Well, it comes from the fact that pi is a constant, right? So maybe we should start with that. So notice that if we are in a circle radius 1, then their definition works, right? Numerically, right? That a is this length because theta is the ratio of a to 1. My problem is that it's theta, while a is a length and r is a length, a divided by r is not a length, it's a dimensionless number. That's the beauty of the radian measure, which I'm sort of shocked at the book for not putting that first and foremost. Okay, so yeah, let me just say that the beauty of this measure is that it's invariant with respect to A and R, right? So if I have the same angle in any circle, if the angle is subtended by an arc A and a circle radius R, then this ratio of A to R will, for that angle, will always be the same measure. So why? Well, recall the definition of pi. Does anybody remember the definition of pi? Oh, Leonardo, you're here. That's good. Nice to see you. Rodriguez. Anybody else come in while I was taking?
I came in here. Xavier Flores.
Torres?
Flores.
Oh,
Xavier
sorry.
Flores. No problem.
Xavier. Okay, right. Flores. And let me make a note of that. Oh, okay, sorry. That's it, huh? Okay. So, yeah, anybody recall the definition of pi? I'm always kind of surprised by how poorly this is understood. People often will say things like 3.14. Well, that's a numerical approximation. It's not a definition, right? So what's special about pi? And that gets right to what's special about the radian measure. Well, I guess I'll just come out and say it then. Some of you are thinking, oh, the ratio of circumference to diameter, very good, Mary, thank you. I figured I could count on Mary. So let's see. Yeah, so this is defined as the ratio of circumference to diameter in any circle. All right, so it's irrespective of the radius, right? It could be a giant circle, a circle around our universe. Well, that's probably too big. How about a circle around the sun, which is the path of our Earth, kind of pretty close to perfectly circular, slightly elliptical, right? Yeah, there is a little bit of a problem, which is having to do with um, what's it called? Physics, general relativity, the theory of general relativity, which has to do with the bending of space-time by mass, right? If there's a mass, especially a large mass, present, then its effect on the space-time continuum is to bend it, right? It's like Leonardo is having a little trouble with the connection. How's it going? Yeah. Okay. So I don't know why I even bring this up. Because it spoils what I'm about to say, which is that, yeah, the space-time continuum is bent by large masses. So the circumference of a circle around a black hole, for instance, which is a giant mass, right? At least a very massive object, may not be giant. It's little tiny black holes that bend space-time in such a way that this definition of pi doesn't necessarily work for that. Kind of pops my balloon about how beautiful pi is. But in the absence of mass, we wouldn't be here. But let's, if we can ignore our tiny masses, then this is true. Okay. Which means what about the circumference? Well, circumference is then equal to, well, 2 pi r, right? 2 pi r, my lord. And, or sometimes we just write c for circumference, right? Is 2 pi r. And that's the whole way around a circle of radius r. Now, the thing is that the central angle subtended by an arc is proportionate to that arc. That's kind of what this is saying. So if it's the whole circle, that's the whole circumference. And the ratio of that to twice the radius. Yeah, see, okay, so the circumference of the unit circle is then 2 pi, right? So we have this factor of 2, which is perhaps unfortunate. There are the Taoists who, rather than working with pi, they work with 2 pi, and they call that Tao. But let's stick with pi since that's what we know, right? So we know that the ratio, well, maybe, is your book going to talk about this? Let's see if they do get around to it. They say the circumference of the circle of radius 1 is 2 pi, so a complete revolution has measured 2 pi radians. A straight angle is measured as half of that, is pi radians, and a right angle has radian measured pi over 2. An angle that is subtended by an arc of length 2 along the circle is measured 2. Okay, since we complete a revolution measured in degrees, 360 degrees measured in radians is 2 pi. And we get the following simple relationship between the two angle measurements, right? That 180 degrees is the same measurement with the unit of radians as pi radians, right? And so the ratio of 180 to pi degrees is equal to 1 radian. Okay. Yeah. So the idea is that, so when they're talking about up here, that, the radian measure of 180 degrees is pi radians. Well, that's saying that the circumference, sorry, the angle measurement to radius is a constant, essentially, right? So I guess what I want to say about this, sorry, not saying it very well, am I? Is that this is a dimensionless number, right? We have circumference is length, diameter is length. If you divide a length by a length, like meters per meter, that's like a pure number. That's not, doesn't have units of meters because you're dividing by meters. Meters cancel out, right? So this is a pure number. So the radian measure, can I say that up here? This is a pure number. It doesn't have units of measure really. I mean, we call them radians, but a radian is actually a dimensionless measure. It doesn't have units of length, doesn't have units of weight or anything else, right? It's just a dimensionless number. And that's actually sort of the holy grail in physics and science sometimes is to get something that isn't tainted by dimension, right? It's just a pure number. So you're measuring some important quantity with a pure measure. And that's called non-dimensionalization. And so this is an example of non-dimensionalization. So let's go back to the text and see what kind of exercises they've got for you. The length of a circular arc. So the angle whose radian measure is theta is subtended by an arc that is a fraction theta over 2 pi of the circumference of the circle. Thus, in a circle of radius, okay, so here they're getting to it, right? In a circle of radius r, the length s of an arc, I called it A for arc, that subtends an angle theta is s equals theta, so it's proportional, right? So I guess I'm going to say that let me say that here, that the arc is to the angle as 2 pi is as the whole circumference is to 2 pi. Now 2 pi is the circumference is 2 pi r, right? By the definition of pi. And so that's how we get r, right? If you solve this equation, so we have a over theta equals r. If you solve that equation for theta, you get theta equals a over r. Is it a two-step process? What? So you've got a over theta equals r, multiply both sides by theta, right? You have a is equal to r theta, which is an important relationship, right? If you want to know the arc and you know the angle in radians and you know the radius, you can find the arc with this formula. Then from that you get the measure of the angle is the ratio of arc length to radius. And that is in fact the proper definition for this thing. So if we get to here, they finally get around to a proper definition. I called it a over r because I called the arc a. They're calling the arc s. Why s instead of a? S, I guess sometimes s is thought of as a displacement in position. And so they're using s as sort of a standard thing. So notice that if your arc has length r, then the ratio of r to r is 1, and so there's an angle with a measure of 1 radian, which is pretty close to pi over 3, right? So about 60 degrees. Is that right? Yeah, pi is about 3.14, so the ratio of pi to 3 is pretty close to the ratio of 3 to 3, which is 1, right? So this is a little bit less than 60 degrees, about 57 degrees, I think. Okay, so the area of a circular sector, okay, so this is a very similar kind of thing. We say that the area is proportional to the central angle, right? So the area of a sector, let me write this out on our paper here, okay? The area of a sector of a circle And what is a sector of a circle? That's like this thing here is a sector, right? Oh, yeah. Okay. Um, and so the sector is a portion of a circle with a central angle theta, right? Is proportional to the central angle. And so what I mean by that is that the area of the sector, let's call that capital A, is to theta in the same way that the area of the whole circle, which we know is pi r squared, is to 2 pi. Right, because that's the whole way around. So the whole circle is kind of like a giant sector. It's the whole shebang. And the central angle of the whole circle is the whole way around, which is 2 pi radians, right? And so this gives us a formula for the area of the circle, right? We can reduce by a factor of pi here. That cancels out, right? So you get the area of a sector is r squared theta over 2. Now, let's talk about dimensions again, right? If theta, the radian measure here, had units of length, then this would be cubic length, right? Because r squared is square units, and theta would be yet another unit of length. So you'd have cubic units, but area is not measured in cubic units. Area is measured in square units. So theta is, in fact, a dimensionless number. And then that's consistent, the units then work out here, right? All right, so that's the formula for the area of a sector. What does your book have to say about that? I think they don't get much wrong in this book, but it's sort of a shocking wrongness for their definition of radian. Area of a sector, okay, so this is if the angle is measured in radians, right? This works, right? You can't use degree measure here. Okay, so then we have circular motion. That's things that go round and round. Suppose a point moves along a circle as shown in figure 12. That's where's figure 12? I don't know. Oh, it must be in the margin or something. Yeah, it's figure 11. Figure 12, okay, like over here. All right. So you're going around and around a circle. There are two ways to describe the motion of the point, of the rate at which the distance is traveled is changing. We've got the linear speed, right? That's meters per second or meters per hour or miles per hour or something like that. So that's the rate at which the distance is traveled is changing. The linear speed is divided by time elapsed. Distance traveled divided by time elapsed. Angular speed is the rate at which the central angle is changing. So angular speed is the number of radians this angle changes divided by the time elapsed, right? And you can find the relationship between angular speed and linear speed by looking at what is the arc length in a circle of radius r. That's going to be r theta, right? So angular speed, this is this omega. This is the same omega that we were seeing as a parameter for a sinusoidal motion, right? We had the sine of omega t plus phi, I think was one of the forms we were looking at, right? So, so omega t is radians per second times seconds, say, and that's going to be radians, right? And the radian measure, that's the arc measure of an angle, right? So finding the linear and angular speed, they find the relationship between, oh, they compute those two. And here's the relationship between linear speed and angular speed, right? And that's because if omega is theta, change in theta per change in t, then you get the change in distance by multiplying the change in theta in radians, right, by the radius. Okay, so let's go to the exercises. I think we're ready for some. And I need to post up some fresh homework for you from my open math. But yeah, go ahead and fill in the blanks here. What do we got? The radian measure of an angle theta. Oh God. Is the ratio, right? So this is just wrong. It's not a length, it's a ratio of lengths. It's the ratio. I mean, who are you going to believe, me or your book? Can we go to let's talk about a third party. Here we go. The third party is the Oxford English Dictionary. How about them? Let's see what they say about. Now, watch, I'm going to be wrong in their book. Where do we find this here? Okay. So, radian. Okay. Notice that the reference is in trig. And they say the usual unit angle is that which subtends at the center of a circle an arc whose length is equal to the radius. So they're talking about 1 radian, right? So it's, for brevity, we shall call this angle a radian. So this is a reference to some historical quote from 1879, right? So they're not giving us another definition of radian. That's all they've got is this quote from historical quote. Okay, well, that's a little bit hedgy, isn't it? How about Wikipedia? What does Wikipedia have to say? Shall we go to Wikipedia? Where can we find Wikipedia? How about in a web browser? Now, mind you, I don't trust Wikipedia either. But, you know, for something as standard as, okay, so we want English, I guess. And we want to look up radian. Notice what they say, the units. Dimensionless, right? Do you see that? Is that too small? Dimensionless, with an arc length equal to the radius. So it's 1 meter per meter, right? So denoted by the symbol rad is the standard international unit. That's the international system of units for measuring angles, and is the standard unit of angular measure used in many areas of mathematics. The length of an arc of a unit circle is numerically equal. That's true. They are numerically equal to the measurement, but not actually equal, right? So it's the same number, but it's a different dimension because it's dimensionless. Okay. So they give you a little history here. And, you know, you might want to read up on that. What's going on? Yeah, so they're giving you some, the conversion from degrees is, so pi radians equals 180 degrees. So while this ratio is not numerically equal to 1, it is conceptually equal to 1, right? It's a conversion factor. So, you know, if you want to convert from degrees to radians, this is what you multiply by. If you want to convert from, sorry, if you want to convert from degrees to radians, right? If you want to convert the other way, you multiply by the reciprocal of that, right? Okay, so dimensional, although the radian is a unit of measure, it is dimensionless in quantity, right? So to call it a length is just wrong, right? Because a length is not dimensionless. This can be seen from the definition given earlier. Okay, and so on. All right, I'm not going to belabor it. But yeah, except in as much as they skip over this first problem here, because they're just giving you the wrong idea. Okay, so suppose that a point moves along a circle with radius r as shown in the figure below. The point travels a distance s along the circle in time t, then the angular speed is Well, omega equals theta per t. So you'd write theta per t. The linear speed is r theta per t, right? So that's s per t, and s is r times theta. The linear speed is the length as well as the same. Yeah. Oh, okay. So that's r omega, right? V is r omega. So they're just reminding you of that formula. Okay, convert from degrees to radians. So should we try a few of these? I like 36. 36 is a cool one. Let's do that one. Why do I think it's cool? Well, so we have, this is 6.1. Number 6. And they say convert 36 degrees to radians. I'll abbreviate rad. Okay, so the conversion factor, well, we want to divide by degrees so that the degrees cancels out, right? And what equals 180 degrees? Pi radians, right? Pi radians is the same measure as 180 degrees, just a different unit of measure. In fact, a dimensionless unit. You keep saying that. Okay, so it turns out that 180 is 5 times 36, right? Should we check that over here? 5, that's 30, 150, that's 180, right? So we can reduce by a factor. So this is pi over 5. Yeah. And that's a cool one because we can actually find the exact value of sine and cosine in terms of radicals there. And not only can we find them, but it's called the golden ratio. So how cool is that, right? We'll do that a little bit later. I don't want to do it now, but we can look forward to doing that at some future time. How about 3,600 degrees? That's number 14. Well, same thing, except it's going to be I guess 20. Yeah, 100 times pi over 5 is 20 pi. That's a lot of pi. That's enough pi for everybody. I think everybody can have 2 pies today. I don't know. We look at the gallery view again. We're up to 8. I guess people are worn out from yesterday's exam. I don't know. Carlem had to go to work, and maybe she's still having to cover for somebody at work, which is a crime. They should be made to pay her like 3 times her regular rate if you're taking her out of class. Should be a law. Gavin, how about it? All right. Speaker. All right. So let's go on. We've got some problems over in the second column here, from radians to degrees. Okay, so how do you do that? Well, I'll pick out a few here. How about number 19? Today is the 19th, so here's number 19. This is 6.1, and we've got 5 pi over 6. What is that in degrees? Well, you can kind of see it on the circle, right? Pi over 6 is what? That's 1/3 of the way to pi over 2. Pi over 2 is 90 degrees. So 1/3 of 90 is 30 degrees. And here we got 5 30-degree things. That's 150 degrees, or 30 degrees shy of 180 degrees. But let's show explicitly the conversion factor, which is the reciprocal of the conversion factor we use to convert from degrees to radians. To convert from radians to degrees, we multiply by the reciprocal of that, which is 180 degrees divided by pi. And the pi's cancel. And 6 goes into that 30 times. So you get 150 degrees. And does that comport with what we know about the circle? I hope so. So here's our circle. So now we can start talking, 30, 60, 90. So this is pi over 2, which is 90 degrees. This is 0. This is pi. And we have our 1/3 of 90 degrees is 30 degrees, or 1/3 of pi over 2 is pi over 6, right? So this angle here, we can say this is 30 degrees, but it's also equal to pi over 6 radians, right? And we can sort of, march in regular steps of pi over 6 around the unit circle. So here's 2 pi over 6 is pi over 3, and so forth. And let's sort of divide this perfectly evenly spaced hash marks around the outside of the circle. So this is 4 pi over 6, which reduces to 2 pi over 3. Getting used to these guys. And this is then where we are, right? 5 pi over 6, which means we've got 5 30-degree increments, right? Each one of these is 30 degrees. 5 of them makes for 150 degrees. And that's good. How about number 28? This is negative 13 pi over 12. Oh, yeah, see, pi over 12 is sort of the hidden measure, right? Because if we go to here, this is pi over 4, then this bisects a 30-degree angle. So pi over 12 corresponds to a 15-degree angle, right? And so if we have evenly spaced points around the circle, we get this pi over 12 here and this 5 pi over 12 here, right? And then those are perfectly evenly spaced dots marching around the outside, right? So if we have 13 pi over 12, well, and negative, so that's going to be clockwise, right? So you're going to go 12 pi over 12 will take you to negative pi, which this is also negative pi over here, right? It's coterminal, going clockwise instead of counterclockwise. And then another pi over 12 would take us to here. Which is negative 13 pi over 12. And that's, 15 degrees more than negative 180. So that's going to be negative 195 degrees. But let's verify with our conversion factor. So 180 degrees divided by pi radians. The pi's cancel out. We've got, does 12 go into 180? Yeah, 15 times, right? So we check that, 12 times 15, that's 30, 150, that's 180, right? Oh, sorry, a little bit off camera there. Right? So 12 goes into 180 15 times. That's a 15-degree measure. And we got 13 times 15, right? So it's negative 13 times 15. 12 times 15 is 180. So this is negative 195, which I suppose you could verify by other means, huh? Coterminal angles is the next little section here. The measure of an angle in standard positions given. Find 2 positive angles and 2 negative angles that are coterminal with the given angle. Let's just jump to 34, huh? Do the last of that little batch. So number 34 says, find 2 positive and two negative, and two negative angles coterminal with a given angle. Coterminal. 45 degrees. It's negative 45 degrees. So that's down here, huh? So I sort of mark the point with the degree measure of the, all right, so that's negative 45 degree angle there, which is equal to negative pi over 4, right, in radian measure. And so what's coterminal with that? Well, you could add 2 pi. So negative pi over 4 plus 2 pi. Well, that's 7 pi over 4. Negative pi over 4 plus 4 pi, right? Any multiple of 2 pi will get you. So we want another 8 pi over 4, which will give us 15 pi over 4. What if we subtract 2 pi? That will also give it once around, right? And so that's negative 9 pi over 4. And if we subtract 2 rotations, which is 4 pi, we get another negative 8 pi. That's negative 17 pi over 4. And what are these in degrees? Well, this is 45 degrees short of 360, so that's 315, I think. So the degree measure. See why it's important to write degrees? If you don't write degrees, it's assumed they're radians, right? So don't, if you mean degrees, put in the little degree sign here. So then this is yet another 360 around. So that's going to be 675 degrees. That's 45 short of 720, which is twice 360. What's this? In degree measure, it's going to be 400, negative 405, right? Because you got 360 negative plus another 45. And then I'm going to subtract 360 from that and get negative 765. Is a degree measure for that? All right. My internet was down yesterday, says somebody. Is there a way I can still turn in the exam? Yeah, just email it to me. Sorry about that. Damn thing. Yeah. So finding a coterminal angle. Okay, I think we kind of did that. All right, let's say we're done with those. Circular arcs. Find the length of the circular arc, the radius of the circle, and the central angle. Sure, let's draw number 54. You get, I draw a circle and then let me reproduce that here. Okay, so basically here's the center of the circle, and they draw a circle of radius 5, and they say that this is 140 degrees, so that's like 90 plus 50. I'm going to say that's, about there. Not meant to be accurate. And they say this is 140 degrees. Certainly is obtuse, kind of like me. And so they want to know, what is this arc S extending around from here to there? So I guess there's a couple of ways we could compute S here. We know that the circumference of a circle of radius 5 is 10 pi, right? 2 pi r, where r is 5, that's 10 pi. So we could find the length of this and subtract it from 10 pi. Or we could, find this angle here. What is that? 360 minus 140 is 220. Convert that to radians and multiply by the radius of the circle, right? So S is equal to theta r. Now, if theta is in degrees, then you have to convert that to radians, right? So let's plug in 220 degrees times 5 times pi divided by 180 degrees. Right? So the degrees cancel out. Whoop, off camera there. The degrees cancel out, right? We got degrees divided by degrees. So the degree measure cancels out and we get a length, right? Because 5 is not a pure number. 5 has units of length. Do they say what that length is? They don't. This is 5 what? I don't know. They don't say. Okay, but it's like meters maybe, or miles, or kilometers. Okay, so we can reduce by a factor of 10. Then we got 11 ninths, 55 ninths. Okay, so this is 55 pi over 9, and that's units of length. That's a 9 down there. Just reduced by a factor of 20, huh? I don't think we can do better than that. I suppose you could approximate that as a decimal, but why bother, right? Alrighty. What else we got here? A few more like that. How about 62? Find the radius r of a circle if an arc of length 20 centimeters subtends a central angle of 50 degrees. Okay, so that's number 56. Oh, sorry, 62. Number 62. Let's take that over to the workbench here. And you see, let me just restate it here. Find the area of a sector, sorry, find the radius r of a circle if an arc of length 20 subtends a central angle of 50 degrees. Well, it's going to be bigger than 1, I think, but let's draw a picture. So let's start with the 50 degrees because that I can eyeball that pretty well. So 45 degrees is about like that. So I'm going to say a little bit more than 45, maybe like that. Doesn't have to be accurate, right? Oh, but I do have a protractor. Let's see, how accurate was I? Oh, a little bit too big, huh? The idea is trying to look to see where Where are we on the protractor? We're a little bit bigger than 60. Can you see that? This is 50 here. So we're a little bit bigger than 50. Closer to 60. 60 is up here, right? But that's not a problem. We can just say label this as 50 degrees. And now it is 50 degrees. We don't know what R is, but we know that this length here is 20, right? And so we get the radian measure of 50 degrees by converting with our conversion factor. And what, 5/18 pi? 5 pi over 18. So that's the radian measure of that 50-degree angle. And we know that S is equal to R theta. Or we can say what? R is equal to S over theta. If you know two of those quantities, you can find the third, right? And we do know two, so we can find the radius as 20 divided by 5 pi over 18. So R is going to be 20 times the reciprocal of 5 pi over 18, which is 18 over 5 pi. And what's that on a Thursday? 72 over pi? I think that's right? 5 goes into 24 times. 4 times 18 is 72. And then you got pi in the denominator. Is that allowed? Can we rationalize the denominator here? Pi is irrational, right? No, you can't. If you have a radical in the denominator, you can multiply by that radical, like square root of 2, right? And rationalize the denominator. You can't rationalize pi that way, though. It's not an algebraic number. So could you approximate that? Well, it's a little bit bigger than 3, right? So 3 goes into 72, what, 24 times, is that right? Yeah. So that'll be a little bit less than 24, like maybe 23, I don't know. We could use a calculator. Do we have a calculator? Sure. Calculator. This is the Microsoft calculator. So if I say 72 divided by, where's pi? I've never been a big fan of this calculator. I can't find things on it. 72 divided by pi. You see pi?
It's in the top row on the left. Down a little bit. And then to the right.
Oh, I see it now.
There
I'm
it
just
is.
blind, aren't I? Yeah. Okay. Thank you. So yeah, it's close to 23, right? 22.9. Right. Okay, whatever. What else we got going here? Area of a circular sector, right? So let's do a few of those. How about, I don't know. Oh, there's some more down here, huh? 64. Find the radius of each circle if the area of the sector is 12. Okay, so number 64. I need a new sheet of paper. And I'll draw a circle to reproduce that picture. And here's the center of the circle. And we've got a sector of radius of area points. Oh no, the central angle is 0.7 radians, right? Which they draw something like this. That means that the arc is 70% of the radius. Does that look about right? Maybe about like that. So this is 0.7. Do I need to write radians there? Well, radian is a dimensionless quantity, right? So we could just write a pure number, 0.7. Okay. So is that enough information? We don't know the radius of the circle. Oh, we know the area of the arc. Okay. So this is number 64A. If the area of sector, how do you denote a sector? Is it like AOB? Maybe like that. I'll put the word sector here, then it's unambiguous. Equals 12. Then what's the, remember the formula? Theta r squared over 2 equals 12. And we know theta is 0.7. So we have one unknown, which is r. And when we go to extract roots, we'll take the positive root because our radius is always positive, right? So r squared is going to be 24 over 0.7 or 247ths. Does that simplify it? No, 24 is not a multiple of 7, right? So we're just going to have to take square roots and say r is square root of 240 over square root of 7, which begs to be simplified, right? Does 240 have a perfect square factor? Sure. 16 is a factor, is that right? Yeah, 16 times 15. So this is 4 times the square root of 15 divided by the square root of 7. And properly speaking, we can rationalize the denominator here. And we get 4 times the square root of 105 divided by 7. That would be the simplified radical form for that radius. Whatever, right? You have to do simplified radical form. Only if it says so. In general, I tend to go to that, right? So what if it's the central angle is 150 degrees? Okay, let's draw another circle. We could reuse the same circle, but circles are cheap. See how cheap that is? You get like a circle for nothing. And 150 degrees, well, that's 30 degrees short of a straight angle. So I'm going to eyeball that as something like this. How close did I get? Here's, can you see that? Yeah, that's pretty dead on, huh? Oh, you can't see the 150, yeah, but it's 150, yeah. So this is 150 degrees. So the area is equal to pi, theta. The formula is theta r squared over 2, right? And that equals 12. So theta is 150. That's 12. Oh, sorry, over 2. And so r squared is equal to 12 over 75, which reduces to 4 over 25. And so r is 2/5, right? Taylor, no, I didn't see you. Okay. We're now into the 13th hour. Is everybody happy? Long pause.
Yeah, we're all really happy.
Well, you shouldn't be. Sorry, I really appreciate you saying something. I so often speak into the void, and I do appreciate a response. But you shouldn't be happy. So, because I deliberately made a mistake here to see if you'd catch it. So I mean, because I see this mistake a lot, right? That people sort of plug into the formula. Oh yeah, the angle is 150. Well, 150 degrees, right? And this formula only works if theta is in radians. You can't use degrees in this formula. All right, so I think we saw before that this is 5 pi over 6. So yeah, this is all kapooey, right? That's all wrong. And sorry to sucker punch you that way. That wasn't very nice. Okay, so 5 pi r squared over 12, I guess, because 5/6 times 1/2 is 12 then. That's equal to 12. Okay, so we've got r squared is then 12 squared over 5 pi. Huh? Yeah, and I think that's a lot bigger than 2/5. So when we go to take the square root, we'll get 12 divided by the square root of 5 pi, which we can rationalize the 5, but we can't rationalize the root pi. So we can say this is 12 root 5 over 5 root pi. But you can't simplify that further, really. But let's compare this. So this was like 0.4, and I don't have a good sense for how big that is. So let's go to our calculator, see if we can compute it. Huh? So can we clear everything here? Okay. So this is 12 times square root. Where's the square root? Do we have to go second here and get a square root somewhere? Is there already a square root here? I can never find anything on this calculator. So they got white root, they got cube root. I don't see a special square root button. Okay. So we want the square root of 5. So let's clear this out and do that first, right? So I'm going to say, how do you do this? You say 2 cube root square root, so 2y root of 5 equals, that's not the, no. Oh, oh, that is square root. Okay, I don't know how, wasn't saying square root before, was it? Maybe it was, okay. So let's clear this out and try again. 5 square root, that's the square root of 5, right? 2.24 approximately. And so that's times 12 equals, now we're going to divide by 5. We got 5, we want to divide by the square root of pi. So we're going to divide by square root pi. 1.7, okay. Does that seem about right? Yeah, I think that's about right. So I'm going to write here on our paper, this is approximately 1.7, which is, more than 4 times as big as 0.4. So, you'd be way off. If you were an engineer, your bridge would fall or whatever. Or maybe it'd be super, super strong, much stronger than it needed to be, depending on how you get. Yeah. what's going on, which who knows, right? Okay, so we want to be here in the book, and how about this one here with the circles? This is kind of fun. The area of a sector of a circle. So we've got circles with radii 1, 2, and 3 are externally tangent to one another, as shown in the figure. Find the area of the sector of the circle of radius 1 that is cut off by the line segments joining the center of the circle and the diameters of the other. Can we reproduce this picture? So we want a circle of radius 1, 2, and 3, huh? Okay. Let's see if we can do that. So I'm going to take my protractor here with a ruler on it and say, here's a 1-inch radius, right? Oh, 1, 2, and 3. So I'm going to say that's 2 ½ inches. All right. So this is going to actually be 2. Otherwise, it'll be too big, huh? And then 3 ½ inches, we'll count that as 3. And we want that to be, okay, so I'm going to draw a line through the center. What happened to my straight edge? Oh, it's right in front of me. And then line these up like so. So that would be our circle of radius 3. And then the center of that circle is here. Center of this circle is here. And so this is 1 and 2. Oh, sorry, 2 and 3. Are we out of time? I'm afraid we are. 2 and 3. So I want something that's 1 unit further. So this is going to be 5, and this is going to be 3, and that's going to be, oh, it's a 3, 4, 5. All right. So this is going to be a right angle down here somewhere. Oh, no. It's kind of hard to figure out where to draw that, right? I guess, yeah, it's a right angle, huh? So it's going to be inside of a circle. If we draw the circle of radius 5 here, and I think the same circle here. What am I doing? I don't know what I'm doing. We're out of time. I'm trying to draw a circle of radius 1 down here that will fit. Let me just fake it. So I want a ½ inch circle. So it's a tiny little thing down here. So I'm just guessing and checking here. Okay, let's say that that's good. Oh, sorry, it's off screen too, huh? And so here's the center of this circle. If I join these two things, you notice that it goes through this, the point of tangency, right? Same thing over here. And so this is 2 and 1 and 1 and 3. So that's a 3, 4, 5 circle. So it satisfies the converse of the Pythagorean theorem. And so this is a right angle here. And we could find the area of that sector is r squared theta over 2 is going to be 1 times pi over 4, right? So that's the area of the sector we want. Okay, I'm going to set up some my open math for you right after we quit here. Let me ask if there are any questions before we adjourn for the 12th week. I do have office hours from tomorrow at 10. I'm not sure where I'm going to be, but I will be on the internet. Can you zoom in a tad more? I'm not sure where. Yeah, here. That might have been a while ago, huh? Uh-huh. Right. Okay, everybody. Well, um, have a very nice weekend. Um, your 12th weekend. And so we can start counting the 12 days of Christmas soon. The
Thank you,
7 days of
Professor.
Thanksgiving. Yeah. All right, everybody. Bye for now.